modeling of cleavage in high-strength use with a parametric study on the microstructures. Our research focuses on cleavage, which is a brittle and transgranular fracture and related to the lower shelf fracture toughness of steels in the transition curve. So we are more interested in the initiation of the crack, and because the crack propagation is occurs in a very rapid speed, so we are focused on the fracture toughness at the initiation rather than the propagation of the crack. And there are several challenges in the modeling of cleavage, and the most important one is because cleavage is very sensitive to the microstructure characteristics. And even though there are some simple ways to relate the fracture toughness, the fracture stress to for example, the grain size through the Hall edge relationship, or there are also like the RPR model to estimate the cleavage stress at a certain distance before the crack tip. But this kind of model is not straightforward to apply on more complex microstructures. For example, for the high-strength steels, there are kind of last structure in the at the macro scale. Here it shows per oscillate grain of the high-strength steel, but you can see there are also a lot of last log and packet inside of the per oscillate grain. So there is an inconsistent definition of what is the grain boundary of the high-strength steels. And the motivation of our research is we perform the numerical simulation based on the microstructure information to predict the toughness of the steels. So we can estimate the performance of the steels and to improve the structural steel design. This presentation will present a parametric study on a quenched and tempered S690 steels, which has this hierarchy substructure. And there are two microstructures that we are interested in. Well, the first one is hard particles that initiate the brittle crack. And for this type of steel, we found that's the inclusions that initiate the crack. The second microstructure is grain boundaries, which can act as resistance to the microcrack propagation. So here we will have three types of grain boundaries. The first one is per oscillate grain boundaries. The second one is packet boundary, and the third one is block boundary. It is in general found that the per oscillate grain boundaries they offers the kind of strong resistance to the crack propagation. For packet and blocks, there are some studies found they can also arrest microcrack propagation. But there are also papers found they cannot arrest the crack. And there are also findings like the packet size and the block size are in a linear relationship with the per oscillate grain size. So here in our model, we use the per oscillate grain size to represent the total effect of the crack resistance. And because the grains and the hard particles will both influence the yield properties, so we also perform a parametric study on the yield properties to the fracture toughness. Our modeling approach is based on a so-called multiple barrier model of the micromechanism for cleavage. It is assumed that there are three macro events that related to the initiation of cleavage. The first event is the nucleation of a microcrack at a brittle particle, which is based on a critical stress criteria. The second event is the propagation of this microcrack across the particle and matrix interface. And this is specified by a criterion that related to the particle size, dc, to the stress state of the matrix. The third event is the propagation of microcrack across the grain boundaries. And the criterion for this event relates the size of the grains to the stress of the matrix. And here there are three parameters in blue. They are the cleavage parameters that determine either the critical stress or a relationship between the stress and the geometry of the microstructures. So and for the so both the three events are based on stress criteria, and there are two types of stress used in the equations. There is one stress, the sigma for the matrix. They are the stress distribution in the matrix, and it's calculated from the finite element analysis of the fracture test. So here, for example, we have a 3-point bending test, and we first assume there is no crack propagation, and we calculate the stress distribution at each load level, which is represented by the CTOD value. And then we can estimate the fracture probability at each load increment based on the calculation from the stress field. The second type of stress is the stress in the hard particle, and it is calculated from an analytical equation from the stress of the matrix. And it is related to the geometry characteristic of the inclusions of particles. There are several inputs for the model, and here I want emphasis on the input of microstructures. So here we are using two types of information for the microstructure. One is the pre-oscillate grain size, and another one is the inclusion size. For the pre-oscillate grain size, we are measuring them from EBSD scan. We reconstruct the pre-oscillate grain and measure the major axis of the grains. So here the point plots, they are the measurements from the scan, and the solid line is the fitting to a combined function of log-normal function and the parallel function. For the inclusion, we did a similar work. So we measured the inclusions from EBSD scan, and for each inclusion, we measured the diameter of from the geometry, and we are fitting with this same equation. And then we are using this equation in our model. So to fit this to estimate the cleavage probability based on these three equations. We are using this method to determine the cleavage parameters. So we can use those cleavage parameters to predict improve the microstructure of stools. So here the input are the finite element analysis, which generate the stress distribution for a certain load increment. And we have got the microstructure of the grains and the inclusions. And we assume the inclusions are randomly distributed in front of the crack tip. And for when we assume there is a certain value for the three cleavage parameters, we can simulate the fracture probability in terms of CTOD values. And we can compare with the experiments data. And among the three cleavage parameters, they are not the parameter we can directly measure from experiments. So for one parameter, the KPM, which is the crack arrestability of the interface between particle and matrix, we are measure this value from fracture surface analysis. So we found here the crack initiator from the fractured specimen, and we found what is the minimum size that can initiate the crack. And we can calculate the stress level based on the location of this particle, and we calculate from this fracture criteria to determine the value of KPM. So for the other two parameters, we are using the maximum likelihood fitting to determine the value from a comparison between the experiments. And the experiments we are using include both the deep crack and the shallow crack of the 3-point bending specimens. When we have these three cleavage parameters, we can use them to give new predictions for an improved microstructure. So here we refer as received material as the base material. And we are using a heat treatment to change the microstructure. So first we did a parametric study using the model. So just to simply assume there are no correlations in those parameters. There are basically two effective ways to improve the fracture toughness. One way is to reduce the amount of hard particles. So in our steels, they are the inclusions. And another way is to reduce the grain size. So here we study how effective are the two ways to improve the fracture toughness. And here in the vertical axis, they are the predicted CTUD value normalized by the base material CTUD value. And so for the same, for the removement of the hard particles, you can see they indeed increase the fracture toughness, but it's only very effective when you remove most of the hard particles. And for the reduction of grain size, it's very effective. Even if you just reduce it by 20%, it can lead to a very significant improvement of the CTUD value. But of course, the grain size is associated with the flow stress. Based on a hot pouch relationship, we know that when we reduce the grain size, the yield stress will also be increased, which should be detrimental to the fracture toughness. So we also perform a parametric study to estimate how much will be this effect. And it found that the increase in the flow stress, well, they did decrease the fracture toughness, but the effect is much smaller compared to the refinement of the grain size. And those parametric studies are assumed there are no correlation for the microstructures, and they assume the grain boundaries are the pre-oscillate grain boundaries. However, from the very beginning of the presentation, I showed there is a hierarchy substructure of the high-strength steels. So for the real material that we perform such heat treatment to decrease the grain size, we found there is also a change of the misorientation angle of the boundaries for the material. And for the pre-oscillate grain boundaries, they are in a range between 30 to 40 degrees. But we saw there is a much decrease for the very high misorientation angle grain boundaries. And those boundaries are the block boundaries and packet boundaries. So it means there should be a kind of difference between the prediction and the experiments. And we want to use this model to estimate how much is the influence of those very high angle grain boundaries. So here we decrease the grain size by 40% and increase the flow stress about 13% by using this heat treatment. The phases and the inclusions are immense. So here are comparison between experiments and simulations. So first we are simulate the reduction, decrease of grain size by 40% with the same increase of flow stress of 13%. And this from simulation, it shows this already in ductile fracture mode. However, compared to the experiments shows even though the fracture toughness is improved, it's still at a very low range. It's still at a very brittle fracture mode. And it means assume this grain refinement is not as effective as we simulated. And it's by comparing the experiments and simulation, we found the experiments is more close to a grain refinement of 20% instead of 40%. So our conclusion is we are using this multiple barrier model to quantitatively capture the microstructures effect on the fracture toughness. And when we apply this model to a heat-treated material, we found we can estimate how effective is the grain refinement to improve the fracture toughness. And we found the grain refinement is not as effective as we expect. It's only about 50% from expectation. And this low effectiveness is due to the difference of the very high angle misorientation grain boundaries, which are related to the block and the packet structures rather than the pure oscillating grain structures. It's it is not so direct to quantitatively model the fracture templates purely from the block and Carey boundaries. So we are still working on try to find a way to represent the effect of those substructures by using this model. Perhaps from the cleavage parameters that we define the resistance of those boundaries. Thank you for listening, and if you have any questions, you're welcome to ask me or later to also contact us. Thank you.
Thank you very much. Again, if there is one small question, we can make it. If no, then thank you again for the presentation, and we can proceed to our fifth presentation.